I want to make a short video about something we talked about in class today. We had a situation where we wanted to find we had a force and a moment. We had actually reduced a system of I think just forces to a force and a couple. So we got a force and a couple, and I wanted to find break up the couple, express it as the sum of two vectors, one parallel or anti-parallel to the force, so along the line of action of the force, and the other one perpendicular to that line of action of the force. I want to look at a really simple case of the same thing, so a special case of that situation where the force happens to be along the z-axis. So I want to call this the x-axis, the y-axis, the z-axis, and the moment is in some other direction. We'll say one that has a projection on the xy axis, xy plane. It looks something like this, so we can think of that one as being made up of m perpendicular plus m parallel. These are vectors. I could have left it labeled the way it was. It would have meant this double-headed arrow. Sorry about the handwriting. Times the magnitude m, times the component m perp in that direction, or you can look at it as the vector. So I've labeled it as a vector in this time, in this case. So what we said, you want to find the component of a vector along another vector. Well, you got to separate out the direction of the other vector. So get the pure direction, which is the unit vector. It's the unit vector in the direction of f, which I just get as the magnitude of f divided into f, or f divided by its own magnitude. And also I take the total m vector, that's this one by the way, dotted into that unit vector, and then multiply this resulting scalar times the unit vector itself, and I've got m parallel. And then from the vector addition diagram that we got here, we know m itself is just m parallel plus m perp, and maybe I'll make it more directly associated with the diagram that I got, because I got them head to tail this way. So first m perp and then m parallel, so I'll put them in that order to correspond to the diagram, but obviously the order doesn't matter. And so m perp is just m minus m parallel. In our problem, we were trying to find the wrench equivalent to a bunch of loading consisting of, I think it was just a bunch of forces, but yeah, it was three forces. And the equivalent loading was a moment and a force applied at the origin of the coordinate system we were working with, and we wanted to turn that into a wrench, which is move the force around to get rid of as much of the moment as we can, and you can only get rid of that component of the moment that is perpendicular to the force, namely m perp as we see it in this diagram. This one, no matter where you move that force around, you can't have it cause that moment about point O, the m parallel. No way to cancel that out. So we wind up with a force at a different location and m parallel, and that's referred to as a wrench. So in this trivial case that I'm looking at here, this all still applies, but you know the answer. If f is say 10 newtons times k, and say m happens to be 4 newtons times meters times I plus 3 newtons times meters times j plus 5 newtons times meters times k, then the component of m that is in the direction of the force is just this 5 Newton meters times k, because the force is in the positive z direction. In this particular case, I'm giving a real simple example, it's in the z direction. And the thing is, our general answer better give the same result. Oh, and by the way, the part that's perpendicular to the force would be this piece right here, which is my 4 Newton meters along I plus 3 Newton meters along J. So this piece is M parallel, the vector, and this piece, the part that's perpendicular to the z-axis, is just M perp. So we know the answer, just want to make sure that the fancy way of getting at it also works. Well, take a look at it. What is U sub f in our case? Well, it's none other than k. It's the unit vector k. For this special case, where the f is along the z-axis, the pure direction associated with it is just the unit vector k hat. I should call it k hat. You could get that by dividing it by its own magnitude. Here's f. Its magnitude by inspection is 10 newtons, divided by its own magnitude, 10 newtons, and you're left with k. So the unit vector in the f direction is just k. Now, m dotted into k, without showing a lot of work, it would be this vector dotted into the unit vector k. Well, I dotted into k gives 0, j dotted into k gives 0. The only thing that gives anything is this. K dotted into k is 1, so the whole dot product gives 5 Newton meters, the scalar 5 Newton meters. So this turns out to be 5 Newton meters for the example that I've indicated, and then it's 5 Newton meters times k, because the unit vector in the f direction is k. And so we wind up with just what I said in the first place by inspection, that the parallel component of m is 5 Newton meters times k. So this expression works in general, but we see that so far it's also working in this case. We got m parallel in this case where we can check it. Obviously, if it works in general, it should work in every case. That means it does work in this case. And then let's try to get m perp from this. M perp would be this whole vector, m, minus what we just found to be m parallel, and of course that's going to leave this part. You know, I subtract off the 5 Newton meters times k, this goes away, this part goes away, all I'm left with is this, and that's an m perp is equal to 4 Newton meters times I plus 3 Newton meters times j. So in this case, again, it's like killing a fly with a hand grenade. But we can still use these general expressions, the ones that work no matter what, on this special case, and we wind up with the results that you can tell by inspection anyway. M perp is equal to 4 Newton meters times I plus 3 Newton meters times j. So that was the whole point of this video, and I did want to keep it short, so that's a wrap for this short video about finding the components of a moment, a couple moment, along and perpendicular to a force vector, but all I looked at was a very special case here.